We're gonna get started now. I'm gonna be talking about blockchain, specifically Bitcoin and Ethereum, and some smart contract attacks. So first off, for announcements, there's gonna be social on the quad this Sunday, February 25th at 3. We're gonna do frisbee, play some games. Pull up should be a good time. Yeah, so there's gonna be no technical meeting this Sunday because of that. This is the meeting flag. Give you all a minute to get on that.
No way, crypto meeting, but it's the currency. It's cryptocurrency.
There's a new XKCD.
Oh,
I don't know. I think we just like search it right now.
never.
Yeah, and we'll get the meeting flag back up at the end. So I think I'll get started because there's a lot of content to get through. So first I'm going to start off with like what is blockchain? So it's sort of the alternative to having a trusted institution. So traditionally you might like trust your bank is going to have your money when you go there later, and they're going to keep an accurate accounting of wherever the money's been sent. But what if we didn't need to have like a trusted party? What if we could trust the algorithms behind your money? So the goals of blockchain is we want a decentralized system. We want to authenticate all the transactions, not by trusting that the parties are who they claim they are. We're going to use cryptographic means to ensure that. We want to prevent double spend, meaning that you say you give your coin to one person, they think they have that, but then later you decide to give that coin to someone else. That can't be allowed. We need to maintain the state integrity, meaning we can't go back and say, actually, I don't want to spend that. We're gonna wipe out that transaction. That should not be allowed. And the way that we do that is with public and private key pair encryption. I'll talk about that a little bit more later. Distributed ledger system, and a proof of work or a proof of stake consensus mechanism. I'll talk about that later. And the a peer-to-peer network for nodes on the network to communicate with each other. So I'll talk about probably the two most popular implementations of this. So Bitcoin was kind of like the first decentralized cryptocurrency. It allowed parties to transact with each other using their public key. And the state of the network was validated by cryptographic means, which I'll talk a bit more about later. But basically, there are no more trusted parties. If you send money, there'll be a cryptographic proof that it was you that sent it, and there'll be a cryptographic proof that it was included in the blockchain that everyone has accepted. And the proof of work consensus mechanism is how we know what the current state is of the blockchain. So an example use case is I just want to pay for something, so I'll send money with that. Then Ethereum is asking kind of what if we could extend this concept of a blockchain to something more general, like a Turing-complete application. So allow parties to interact with smart contracts, so maybe like buying NFTs, trading different tokens, even like voting in a governance proposal. So I'll just do a quick like crypto review for the relevant concepts here. So public key cryptography allows you to generate a key pair where you'll generate a related public and private key. The public key you retain to yourself, or sorry, the public key you distribute widely, and that's kind of your identity. And the private key is what you have to maintain private, and that's how you'll be able to authenticate that it's you behind that public key. And the private key is what allows you to generate a signature. So like if you have a message and you want to be like, yes, I approve this message, this is me like authorizing this message, you'll generate a signature using your private key. And anyone can see that this public key says that this message is okay. So hashing is a one-way function that'll take any arbitrary length input and give you a fixed length output. So the useful thing here is that it's very difficult to maybe find one input that matches a given output. So basically, you know that if somebody gives you an input and an output, that input was what was used to generate that output. They probably did not find another input that gave that output. So two hashes, one of them is SHA-256 using Bitcoin, and later KEKAK-256, which has become basically SHA-3 in Ethereum. So transactions are the basic unit they use for interacting with like blockchain cryptocurrency system. Those are what is signed with the party's private key that are like authorized for the party's public key. And this is what actually allows you to modify the state of the blockchain, like send money to somebody, maybe vote in a governance proposal, something like that. The distributed ledger is what records the state of the system. So, and the transactions and all those things. So like maybe your account balances, storage in a smart contract. They're grouped into blocks of transactions that are identified by their hash, and they're chained to include the previous hash. So like if we have this hash here, when the next block is created, we include the previous hash so that we can go back in time and make sure that all the blocks are part of this chain and that all of the contents of those blocks are correct because everything's hashed and you can't find another block that would give the same hash. So proof of work consensus is sort of solving, so who's allowed to create these blocks, right? Because if we like said, this party is the one that's in control of the chain, we're not decentralized anymore. So we need some mechanism for determining what all the nodes in the network are going to accept as being the true state of the like head of the blockchain. So instead of relying on like, central authority, we actually rely instead on the parties in the network having pretty evenly distributed computing power so that no one party is just going to have like way more like hash power than everyone else. So the way that we do that is if we go back, one thing that, oh, I think I deleted that from there. There's actually a nonce in the block that's just a random value that's included so that we get to manipulate the block hash. So basically, we want to make sure that the block hash has enough zeros leading it. And that way we'll know that the miner has done a bunch of hashing. They've somehow found a hash with a really low block hash. And this, because it's a hash function, it's really difficult to determine this, and it will require a lot of compute. And in order to make sure that the blocks are paced at a regular interval, let's say randomly some guy just like buys like, a million GPUs or whatever, right? It'll actually increase the difficulty so that the block is pacing is slowed down to the regular interval, which is like several seconds for Ethereum, I think like 15, and then 10 minutes for Bitcoin. So, and now the last component here is we have this blockchain, that's great, but how do we actually get people into the network so that they can participate? So we use a peer-to-peer network, meaning that just any computer in the world can try to join the network by finding other nodes that are participating in it through different discovery protocols. And once they've discovered each other, what they'll do is any pending transactions, let's say you want to send out a transaction or you see some transactions going through the network, you'll distribute that to the other nodes in the network. Nodes that are mining blocks pull up all the pending transactions that they intend to include in a block, and then they'll keep trying to find that nonce value that gives the low hash. And once they've mined that, if they've found the low enough hash, they'll broadcast the block that includes all of the transactions, the block hash, the nonce, which is the proof of work verification. And then other nodes in the network will accept that block if the proof and all the transactions inside of it are correct. So altogether, this is like a demonstration of how you could send money on like a system like Bitcoin. So what's going on here is Bob wants to send money to Alice, but first it has to get mined. So he'll generate this transaction, he'll sign it with his key. Then he'll send it to the network, which will get received by this miner, who will pool it up with these other two transactions. And then once the miner has found the proof of work, it'll get included in this block, the next block, n+1, along with all the other transactions, and then this nonce that they mined. And then once the miner has created this block, they'll send it to all the other parties in the network, including Alice. And then Alice will see that she now has $10 from Bob because that was now included in this block. So a few attacks on the blockchain is 51% attack. So basically an attacker would be able to sustain a majority of the network's hash power, meaning that they could outmine the network, which means they could actually create blocks faster than the rest of the network does. And because of the way the consensus mechanism works, if you have a longer chain that has valid proof of work, people accept that as being the new state of the blockchain. So what this allows you to do is you can create a double spend attack. We would maybe send that money to Alice, and then you mine a new blockchain that doesn't include the transaction we sent the money to Alice. So Alice thought she had money, but then you're like, actually, no, we're not going to send that out. And then you can send it somewhere else. So that's called a double spend attack. And you could also just generally censor transactions. Maybe some transaction that occurred on the blockchain for whatever reason was really unfavorable to you. You could try to mine a new blockchain longer than the previous one that excludes that transaction. So the reason this isn't, yeah, sorry.
So is there like a certain size of, like, is there a certain like platform size you need to have in order to like prevent these attacks? Like, obviously, if you had a certain amount of GPU to actually take 51% of like Bitcoin's like network, like that probably wouldn't be reasonable. But if you have a smaller coin, like,
Yeah. So I'm actually, next slide, I'm going to talk about a few historical examples of where this has happened. But the way that you try to prevent this is by having mining incentives that outweigh the loss of value if the currency becomes untrusted. Basically, if your currency gives a lot of rewards for mining it legitimately, and the currency is worth a lot, it would make more sense to actually mine it legitimately versus devaluing your currency by doing a 51% attack, because then the currency is not going to actually retain its real value if people don't trust it anymore. And you might not even make that much money from 51% attack if there are really truly a lot of rewards to having that hash power. So it's sort of just a balance. Like, does it make enough sense for me to pay a ton to get a ton of hash power? Or if it's really cheap, maybe it makes sense. So there have been several historical attacks. In one example, an attacker actually multiple spent tens of millions of Bitcoin gold by just sending it to cryptocurrency exchanges, cashing out, and then reverting those transactions to double spend. And Ethereum Classic has actually suffered numerous attacks, including like millions of double spent Ethereum, because miners just weren't mining it anymore. So what you can do is you can go on something like NiceHash. You could just buy GPU hash power, and it might be cheaper than like how much money you gain from doing a double spend attack. So you could literally just like pay like a bunch of people who are mining on NiceHash to compute the proof of works that you need and generate a long blockchain, just make money basically. So yeah, the accessibility of this attack means that you need good incentives to keep miners honest. So here's exactly how a 51% attack would look. So this is just like normal operation of, let's say you send $5 from A to B. Eventually, it'll get, it'll just get propagated along the blockchain. It'll be confirmed for numerous blocks. And at some point, party B will accept, okay, I have $5 because this transaction's been in the blockchain for a long time. But what you've been doing in private is you've actually been mining a private blockchain where this transaction is excluded. So instead, you just keep mining as usual, but just without this transaction that you want to exclude, and you'll eventually outpace. So let's say you mine 50 blocks in the time it takes, I don't know, normal miners, the state of the network to mine 30. What you can do is once you have this really high block, you can broadcast this, your private blockchain, to the public blockchain. And because you've done more work, the public blockchain, they'll be like, okay, sure. Yeah, you have the legitimate blockchain. And it'll accept your block as being true. And it'll just keep building off of this. Except the problem is this $5 that you sent from A to B is no longer in the blockchain. So if B thought they had $5, well, they don't. So yeah, say.
Sorry, so you mentioned that these nouns were generated over a specific period of time to pace it better. How does it get generated, and how can a party, for example, mine 50 numbers ahead of the other parties, if that's the case?
Yeah, so the nonces are just values that are included in the block in order to reduce the hash of the block. So
Right.
like just the hash has a lot of leading zeros depending on what nonce you choose. And the number of zeros is how you pace it. Basically, you're like, okay, if the blocks are getting mined way too fast, we need to make this harder, increase the number of zeros you need to get, because that just means you have to try more nonces before you get that many zeros at the start. Yeah, and the way that you'd be able to, let's say, outpace by like doing 50 blocks when 20 have been mined on the main public chain is you just need that much more compute power. So let's say mining incentives are really bad on the public chain, like you don't really get any money from doing it. There are not going to be many miners there because there's just no profit there. So it'd be really cheap to go on NiceHash and just, for 30 minutes, just buy some hash power and just completely outrun it.
So when you don't have as long of a chain as the one that's going to be broadcasted, do you just try again on the new, like, do you pull it and then try and add yours and push it again?
What do you mean by that?
Like, in this scenario, if we weren't trying to do like a malicious attack and we were just, the initial chain that we were building on to send this $5 was shorter, would we just update our current chain, add our transactions, and then put like?
I guess, yeah, maybe, I'm not totally sure I understand, but I'm gonna go up a little bit to try to. Basically, the miner right now, they have the current state of the network, like whatever the last block is stored, they pull up transactions. And once they mine it, they'll add to whatever the latest block they know, and they'll include all the latest transactions. I don't know if that clarifies it, yeah.
So I guess like if this miner was not the fastest and someone, we had like a second miner.
Yeah, they
and
just
then
lose.
publish theirs, are all of these transactions gone, or does the miner just repeat it and then push it onto the net, like the front of that?
Yeah, so the nodes in the network are supposed to keep track of all the transactions that haven't been included in a block yet.
Mhm.
So if like, let's say another miner mines before you, you'll still remember those transactions because you never actually got to include it on the blockchain. And sometimes what will happen is you might mine a block before another miner tells you about it. And I actually don't remember the exact consensus. I think it's basically just whatever gets first arrival is generally how that's resolved.
So if say a malicious miner were to modify the chain, then another miner can easily outpace and override the whatever they were trying to override.
Sorry?
So if a malicious miner tried to outpace the chain and write some malicious data onto the blocks, the other pool of miners would just outpace it and just
Yeah,
basically
yeah. If
record
the data
changes.
itself is invalid, nobody will accept it and eventually it'll catch up. But if the data is valid, like in this case, there's nothing wrong with this, right? You can have a blockchain that doesn't include a transaction.
Right.
So that's the dangerous thing here is that this is a valid block. The only problem is that people thought these were the valid blocks, but you've just outpaced it and rewritten history basically.
Can you explain how the math difficulty works in this scenario? Does the difficulty have to be the same for this to be pulled up?
Actually, yes, I'm not totally sure how the difficulty is. I don't remember the protocol for the getting consensus on difficulty. I know it takes a while, like several blocks for the difficulty to be updated. So if you're only moving a couple blocks, you probably don't need to pace it. And it's based on the real-time time as well, so you could probably spoof the timestamps a little bit to.
So like if I mined a bunch of blocks with easy difficulties, could I just easily outpace the main?
Yeah,
network?
so the problem with that is that I don't remember exactly how the difficulty is known to the network, but it is known to the network. So if your difficulty is too low, it will be rejected.
Okay,
I think that's,
for like a separate difficulty consensus?
yeah, I believe there is. Yeah, I don't remember the exact protocol for how the difficulty is like agreed upon, but there is a protocol there.
Okay.
Yeah, so I went through that. Okay, so now I'll talk about an attack that specifically focuses on the peer-to-peer aspect rather than maybe the blockchain aspect of these systems. So it's called a Siebel attack, and what it allows you to do is gain disproportionate control over the network by generating like many false identities that all are actually owned by you. So on a lot of these like discovery protocols or whatever, it's actually quite simple to like spoof having maybe thousands of nodes or something like that. So something that I believe has been demonstrated, at least in research on Ethereum, is called an eclipse attack. So basically what you do is by flooding the discovery network with a bunch of your fake nodes, eventually you'll gain so much influence over the network that some nodes might only be connected to your false nodes. And at that point, you filter their view of the network. Because you can, if you're the only, like let's say they think they're connected 20 nodes, but you are all 20 of those nodes. You can just start not sending them updates anymore, and they won't know what the current state of the blockchain is because you blocked their access to it. So there are a lot of mitigations in place for this because it's a very serious attack because you could just say block out all the miners from knowing what's really going on. Like what, for example, the discovery protocol, it favors older nodes. So like if you just create a bunch of nodes, those nodes aren't going to be favored as much by the network. So hopefully older legitimate nodes take precedence. There's also, I believe, kind of a proof of work aspect to some of these discovery protocols. It's not particularly robust in the case of Ethereum, from what I remember, but there are other mitigations along those lines that have worked for the most part. And now I'm going to talk about specifically the innovation that Ethereum brought, which is smart contracts. So these are programs that you upload to the blockchain, are executed by all the nodes and miners in the blockchain. And like all of the state of the smart contracts and all of that is on the blockchain so that everyone knows exactly what like is going on with these smart contracts and can verify what they've done because they're all deterministic. So you can interact with these smart contracts directly through your own transaction, or smart contracts can even interact with each other. Yeah, so these contracts are executed without like a trusted party. The entire blockchain is where the trust is derived from. So for Ethereum, the language of choice is Solidity. So this is an example in Solidity of very useless smart contract. Basically, you have this state, which is stored on the blockchain. It's just a count. You have a get, which will return, this is a method that'll return the current count, increment, and decrement. And these are all public, which means they can be invoked from externally. And basically, I don't know why you'd want this, but if for whatever reason you just needed a counter where you can trust the output of it is going to be held across the entire chain, you can do this and it's verifiable. So now what some attacks on smart contracts are, and this is just normal software, right? So for a while, avoiding like integer like underflow or overflow required special tricks. I believe Solidity compiler now adds guards for that by default. So if your smart contract runs into an overflow or underflow, it'll just revert the transaction so that no harm is done. Another thing is just general logical bugs. I mean, there are innumerable types, but maybe one sort of those is like improper access control. Let's say you have like a protected method that needs to only be like executed by, let's say, another trusted contract that's related, but it's actually public. That could be an issue. And just due to the interactive nature of smart contracts, what's called a reentrancy attack, which I'll show an example of later, are pretty common because they can call into each other at any time. So an attacking contract, I guess what a reentrancy attack is an attacking contract will unexpectedly re-enter the victim contract while the victim contract was executing. So the victim contract might be doing something, then in the middle, your attacker contract will gain control and call the victim contract again. But the victim contract was expecting just to finish its execution first. And the problem with smart contract attacks is kind of what one of the goals of blockchain is once a transaction's in the blockchain, you're not going back. So if, let's say, somebody steals a bunch of money from your smart contract, there's no one to go to fix that. It's gone. So that's why smart contract security is really important. So I'm going to talk about reentrancy attack. So in this case, this guy is representing a malicious smart contract made by an attacker. So what this malicious smart contract will do, because contracts can invoke other contracts, it'll call this withdraw method. The withdrawal method will look up the balances of the sender. Let's say the sender had 100 of whatever this is. 100 is more than 0, so we pass. And then what we do is we're just trying to pay the, like this is supposed to basically be some sort of bank, right? So you put some money, some actual Ethereum into the bank. They'll keep track of that. And then they'll send that money back to you when you call withdraw. But the problem with call is that call actually returns, it'll give you the money, but it'll also call your smart contract. And because your smart contract, it's Turing complete, you can do what you want. What you'll do is instead of executing this, where it'll wipe out your balance, it'll just say withdraw again. I want more money, right? Because it hasn't set your balance back to 0 yet, balance is still 100. It's still 100. And then it'll send you another $100. So now you got 200 already. And you can just keep repeating this recursively, right? Because we never set it down to 0. So you can just get a lot of money this way, right? You can just drain the contract. So in 2016, actually, the Ethereum network suffered an attack on this, and one of their smart contracts, the DAO, was pretty popular at the time. And controversially, because this had such influence over the community, a lot of the community decided that we want to revert this attack, which goes against a lot of the principles of blockchain where, it's supposed to be immutable. It's supposed to be this public ledger where this is what happened and this is how it is. But instead, they actually went back, edited the blockchain to remove the funds from the attacker. So now I guess just a few tools that are useful. If you want to explore like what's going on the Ethereum blockchain, you can look at Etherscan. It'll show you all the blocks when they're coming in, transactions, all of that. You can even do OSINT because you can start to see who's sending money to where. You can try to tie that together. Remix is an IDE that allows you to do smart contract development. I'll try to demo that in a bit. And MetaMask is just how you might manage your wallets, and it also integrates with Remix, so you can start sending transactions to live blockchains if you have like your wallet set up in MetaMask. So some resources here are the Ethereum docs white paper, EVM. So EVM is short for Ethereum Virtual Machine. It's basically the runtime where your smart contracts execute. So it's important to understand that. And then just Solidity docs, because Solidity is the language that you're going to be writing these smart contracts in. Yeah, so this is a recap of the next meeting. So Sunday we'll be doing Frisbee on the quad, and then next Thursday we'll be doing password cracking. So yeah, that's it. This is the meeting flag again. Yeah.
Could you explain a little bit more about how ASICs are used to like mine versus like GPUs like we would buy to like play video games?
Yeah, so I mean, ASICs are now incredibly advanced, several orders of magnitude more powerful than a graphics card is at computing hashes. So remember how hash power basically determines how likely you are to get a block. Because those ASICs are, several orders of magnitude better than a graphics card. If you were the only miner that had ASICs, you would pretty easily outpace the chain just because economically it would just make sense for you to do so. But I don't actually know how much power they use, but it's an absurd amount of power that's being used by these ASICs, which is part of why 51% tech on Bitcoin or whatever is sort of absurd because of how much money has gone into like this mining equipment.
Wait, what did you say? You said
51% attacks on Bitcoin. It's just absurd because of how much compute there is going on there. Like if you're trying to just enter into this, you're not going to.
And so like with that, what makes ASICs so good at mining and computing hashes versus like a GPU? Like, yeah, why are they so powerful?
Yeah, I guess it comes sort of to like maybe a computer engineering question, which I'm not super familiar with, but basically the circuits for actually computing a hash function can be parallelized in silicon much better than they can in like a graphics card. So because graphics card are general purpose architecture, if you just specifically do like the SHA-256 rounds in silicon, you can do that in parallel very easily and scale it massively. Yeah. Yes, are there any other questions about that? I know there's like a ton of content, so I could go back through a lot of these.
Can you re-explain the re-entrancy attack?
Sure. Yeah, so okay, so the purple guy, right? This is representing an attacker's smart contract. So this attacker's smart contract, what it'll do, it'll start, or like at some point, let's say the attacker's smart contract has deposited money into here. So it has some money in this bank,
Sure.
some Ethereum in this bank. But then when you want to start the attack, the smart contract will call withdraw on the victim contract, the bank in this case.
So in this example, the contract you have on the screen is the victim contract.
Yeah, the bank is the victim in this case. We're trying to drain money from the bank.
Okay.
So yeah, we enter the withdraw function from our malicious smart contract. Our malicious smart contract does currently have a balance at the bank. It'll send this money out because it's doing call, which with the value. Call with value means that you're paying money to the caller. So yeah, so like this guy gets paid money by calling with the value. Yeah, so it gets the money back from this basically. But what this also does, it doesn't just send the money. It actually calls the contract. It'll invoke, I think what's called the fallback function on this contract, which will allow this contract to resume like it'll be able to execute whatever it wants at this point because now it has control over execution.
So this is like an RPC almost to the attacker contract?
Yeah,
Like how would you describe the message sender call?
yeah. I guess I would. Yeah, I mean it's sort of just like I guess an RPC in a way. You're just like invoking a method basically. It's something like that. It's like calling a function, right?
So you're invoking the default method of the attacker contract in this case?
Mhm.
And is that because they forgot to specify like a method here? Like what, that seems like a large issue.
Well, okay, so the way that I believe the calling convention works is you just call the contract and then it sort of figures out based on the call data what it should run. But if your contract doesn't really care about the call data, you can just execute something in any case. Or you could have a default case where no matter what the call data is, it doesn't match one of the other function signatures, so it'll just fall through and go to the fallback method.
Sure. So in this scenario, like what? Or I guess I don't really understand. Like, what is the point of calling this other contract? Like, what code is it supposed to be running on the other contract?
Yeah, so in this case, the call is maybe a little bit contrived in this example. A lot of the time, like how I was saying, at last, my contracts communicate
And
with
the
each other.
call is the name of, what is call? Is that like just a keyword?
Yeah, it's just like a general keyword because yeah, let's just invoke the method with some call data, or like just invoke the contract itself with some call. Invoking specific methods and Solidity requires that you have what's called the ABI of the other contract, which basically specifies like the interface for it. So if you wanted to invoke a specific method on another contract, you'd load up its ABI like up at the top, and then you could actually call specific methods with specific types of data, and then it'll actually like serialize the call data to that contract in that format. But in this case, we don't really care about the specific call data because this is contrived. Basically, the idea is we're just paying Ethereum.
Right.
And paying Ethereum does invoke a method if you do it this way.
Okay.
Yeah, but like another examples, I think I saw like one of the CTF challenges. It's like I think if you're minting a coin, it would call a specific method on the caller contract. So you'd have to, or you don't have to, but it would have a specific convention that's calling the parent with. But in this case, there's really no convention because it's just this blank string.
Sure.
Yeah, so because we've returned execution to this guy, we don't follow through here. And then, yeah, we re-enter. We haven't set it to 0 because this line never executed yet. We send another 100 off to this guy, and we just do that recursively.
So in the attacker contract, it's calling the withdraw method again.
Yeah, it'll call that again, and I'll show. Actually, how much time? Okay, yeah, I'll show that in maybe like 5 minutes. How we actually do that. I'll show an attacker contract that will exploit basically this contract exactly, and how it will be able to re-enter withdraw.
So how would you typically prevent this? Would you have to do at the beginning of each function, like make sure that no re-entry attack is occurring?
Yeah, so I guess there's different ways of doing that. I'm not sure, like you could just have some state here, kind of like a mutex.
I never used Solidity.
I think the other trick is just fixing the order here, because you should set it to 0 before you return execution.
Okay.
So a lot of it's just careful ordering, but you could do like a mutex lock or something similar.
Yeah, I see how that could make it very hard to spot.
Yeah, I mean, that's why the DAO got exploited. Because Solidity was very new at the time. I guess smart contract Solidity just wasn't well understood. 2016, pretty new stuff. Yes, I believe it was actually known at the time it was exploited. I think the developers were like trying to like get the contract updated, but like updating contracts is I don't know if update mechanisms had really been used much at that point because the stuff was so new. So yeah, it was sort of like a race against the attackers, I guess, and they lost. But yeah.
All right, that's what.
Mhm. I guess I'll start getting set up for solving the challenge for the demo.
Press the Windows space to switch to party.
Thank you. Alright, wait, where did you have? Oh, it was in the Chrome profile. Okay. Yeah, I don't want to give the solve quite yet in case somebody's like ambitious and wants to solve this one.
What's your setup like? I'll just ask you some questions real quick. Please hold on that.
Yeah, so okay, I'm lazy. I just use Remix for this because it's like has all the tooling built in that you need basically. Like you can compile contracts, and if you have MetaMask, you can literally start sending transactions to the blockchain just by clicking some buttons here. So instead of like, figuring out how to use like, I don't know, ethers and getting that all set up, I'll just use Remix a lot of the time. I mean, I don't do a ton of dev. I'm sure if I did, I'd probably do something more serious, but yeah. Oh wait, how do I get the contract? Okay, so I guess because we are running a little tight on time, I'll get started with demonstrating how you do the reentrancy attack. Okay. Yeah, so right now what I've done, I've just downloaded the Solidity file. Wait, did that work? Wait, how do I import this here? Okay. So yeah, I've just imported the challenge file. This should be just up on CTFD, like if you just look at the challenge store. So this is the contract that we're trying to exploit. So what was it?
Can you zoom in?
Oh yeah. Is that good?
Yeah.
Okay. Yeah, so this is the contract we're trying to exploit. It's very similar to the one I just showed in the example slides, except we're not paying Ethereum here. It's even more contrived. We just do a random call in here. I'm just trying to give a very minimal example. In reality, it'd be calling for some specific reason instead of just randomly calling in the middle. But this sort of reentrance is like an actual problem. So yeah, so this is very similar to the bank. We have a list of balances. The way that we acquire a balance is we must have never opened an account before, or otherwise our balance has to be 0 for the sender, and it's default 0. So what we do is we call open account, and that'll call us back, and then it'll increment our balance by 100. So if you remember from the slides before, what we're trying to do is when we get execution flow from here, we're trying to block this, or what we're trying to do is circumvent this check. So what we can do is we can call this, and when we call this, our attacker contract will actually call open account several more times. But because we haven't incremented the balance yet, it'll still be 0. So we'll pass through here. And then eventually, once we return from here, maybe let's say we invoked it 10 times, we'll fall through all 10 of those times, increment our balance by 100. And then when we go to solve 1000, or when we go to the solve method, we'll have a balance of 1000. So this, again, it's pretty contrived. This is just how we verify that you've solved the challenge. Basically, you have to have $1,000, which wouldn't seem to be possible from this, in order for it to emit this event. And then on our side, we'll see if this event got emitted, and then we'll give you the flag. So I guess I'll get started writing the attack contract for this. I'm just gonna pull it up on the side here just so I don't mess it up. But
Can you explain the
Mm.
string memory message parameter of solve?
yeah, so
Where does that come?
yeah, so when we call the solve method, we get to specify the string.
So the attacker would specify the string?
Yeah, so this is a contrived thing. I'll actually just open maybe terminals to show you kind of what the challenge prints out to you. So yeah, this is what the terminal is going to print out to you. So when you connect to the challenge, it'll say like, hello, your goal is to get rich, get at least 1,000 in your balance, and we'll let you through. Contract is deployed at this address on the Ethereum SIGPwny testnet. So what you're supposed to do is once you've gotten your 1,000 coins through the reentrance attack, you're supposed to call the solve method using the string that's been generated by our server. And then once you've called solve with that and it's emitted this event, the server will know that you've actually exploited the contract.
So there's logic we can't see that will print out the flag.
Yeah, so the flag is printed out by our server, making sure that an event has been emitted with this given string.
Okay.
So the smart contract just has to emit this string somehow, and then they'll give us the flag.
So in no way is the flag embedded in the smart contract.
No, in this case, yeah, no, the flag is not embedded in the contract. It's just in the server. But the point is that somehow you've gotten a lot of money and exploited the contract. So I guess I'll start writing the exploit contract now. Let's just call it exploit. Let me just open up on the side here, the solve. Yep. So contract solve. So what the first thing we'll do is remember how I was saying that you can include the ABI of another contract, which means that you can start to call specific methods in another contract. Solidity will just allow me to import the other contract. Okay, hold on. So yeah, bank.sol. And what this will allow me to do is specifically reference the bank contract and call methods on it. So I think it said, oh, sorry, where was the, okay, yeah, so the contract was at this address. So what I'll do is I'll tell it that our contract is at this address. And what this is doing is it's basically allowing me to interface with the bank contract that is deployed at this address. So yeah, what's up? Yeah, bank, yeah. So what I'll define here is the actual like exploit method. So what this will do is I'll actually just do this in one step where I take in the string that our servers provided us. And it'll be public so that we can invoke it ourselves when we interact with our exploit contract. What I'll do is I'll open an account with the bank. So what this is doing is it'll call this open account method and it'll do all this, except I'm going to intercept this. I'm going to take control by defining what's called the fallback function and then external payable so that we can call it from the contract. And what I'll do is I'll do bank.open account. So this is essentially all the final exploit's going to do. The only problem is, we call open account. We just keep recursively doing this. It'll never terminate. It'll just keep, like if you've seen like a Stack Overflow or something when you have infinite recursion, basically that. So the transaction won't go through and we won't accomplish anything. So we have to terminate the recursion somehow. So what I'm going to do is I'm just going to keep track of the count, the number of times that we perform this exploit. I'll start it at 0. I mean, I think it's default that, but anyway, what I'll do is I'll just keep incrementing the count. And as long as that's less than 10, because we need 10 times to keep giving us $100 10 times, then we'll have 1,000. We'll just open the account in this case. Yeah, so this is essentially all we need to do, except in order to tell our server that we've solved it, we need to call solve and then it'll emit this event. So what I'll do is I'll just do, and then our message that we passed in here. And this is actually, I forgot to put semicolon up there. And all right, it works. It's a warning. Yeah, so this is the complete exploit that what it'll do, it'll start off by calling open account. It'll get message sender call, which will invoke the fallback function. it'll 10 times, again, open an account. And then once it's done with that, so once, you know, count is greater than equal to 10, instead of opening account will finally fall through. And then that'll finally fall through on this call. And then it'll just cascade down doing balances plus equals 100 10 times. And then once those, all 10 of those are done, an open account, we'll call solve. And solve will, well, if we have 1,000, should emit this event. So let's see how this works. What I'm gonna do here is open our exploit contract. I'll compile the Solidity. And then, okay, actually, I guess quick aside, it may be some MetaMask setup. I'm going to add the oh wait, I don't know if testnets are okay. Wait, did it add? Okay, yeah, so we have that. I think I might need to enable it in the settings to actually show it. Where is, yeah, show test networks. Yeah, so if you're doing stuff on testnet, you definitely need this on. Yeah, so now this should allow me to switch over to the testnet. Okay, problem is, in order to do transactions on the Ethereum network, you need some Ethereum. So what I'm actually going to do is you'll have to find a faucet. I linked, yeah, I linked it on the, maybe we have to update the description, but I linked a faucet that should be able to give you some SIGPwny testnet ETH. But instead, is it alright if I just like send it on Discord to me and then I'll send SIGPwny? Okay. Yeah. Yeah, so also, yeah, if you don't want to bother registering for yeah, if you don't want to bother registering for like one of these faucets, you can just message me your address and I'll send you a little bit of testnet ETH.
Oh, and you just put your
It's some real-
values. Yeah.
real
Yeah.
Ethereum too.
Why it wasn't working here. So,
Yeah, so what I'm gonna do is I'm gonna send. Okay, so yeah, on my laptop on the side here, what I'm doing is I'm using MetaMask to send 0.01 ETH to this account. Right now the transaction's pending, should solve and like it should
Like
resolve
here.
in
This
a
one actually.
little bit here. All right, do I need to bump the gas?
sure, it's in the-
Then okay, awesome. This is still says pending on my laptop, but that's cool. Yeah, so now I have some testnet ETH that I just sent to Min's laptop here.
Google
So
support
now what we can
also.
do is we can actually switch this to the MetaMask provider. We'll link this account because that's the only one here. And now Remix can actually interact with MetaMask in order to sign transactions and submit them to the Ethereum blockchain. So what we'll do is, because we've just created this solve contract, I'll usually test this locally first, but I know this works. So what I'll do is I'll just deploy it on the testnet. It'll ask me to confirm before signing and submitting the transaction. And then in a little bit, we should see our deployed contract show up.
Your own computer.
Yep, so we have our solve contract. And now what I'll do is it's basically ready to go. I just need to put in the string from our server. So what I'll do is, I don't know if I timed out, so I'm just gonna reopen this. I'll copy this string, send it to the exploit, and I'll confirm this transaction again. It'll sign it with the private key through MetaMask. And now we just have to wait, it's pending. And it's, if we want to look at this on Etherscan, we could see our transaction got confirmed. And if we look at logs, this is what that event was doing. it's actually created this, if I put this to text, oh wait, hold on. This is the string that we're given by the server. And now if we go back here, I'll just press enter and the server prints us the flag, because basically what the server did, it just looked up the logs of this contract. It saw that the correct string is present in those logs, and then it decided to give us the flag because we've proven that we've exploited the contract because we could send this. And in order for it to appear in the logs, we must have a balance of 1,000, which was verified. Yeah, the logs is this event that I'm talking about being emitted here. So, but in order for us to emit that, we must have had 1,000. Yeah, I guess any questions on this reentrance exploit? I guess I don't know if I can I split screen here? Is this like VS Code? Can I just drag this? Oh, okay. Oh wow. Yeah, so this is like the reentrance attack and the bank contract. I guess I'll also I could go back to the slides.
Oh, so instead of login, this
Wait, where is
what
the
slide
yeah, yeah.
it verifies you've been up.
Yeah, so this is basically the same thing we were doing here, where our malicious contract, the contract that we called like exploit, is basically the purple guy.
Forcing to. Yeah, so it's getting hash from the computer, which sucks.
Thank you.
Explain the OSINT one, like, what are we looking for?
Okay, sure. Let me pull that one up.
What API? Found it.
Okay. Wait, did I? Okay, hopefully I linked the right thing in there. I think I should have. Wait, let's open up on CTFD here.
Oh, I did just verify. You should use or could you sign on the
Oh, I mean, I'm already in the admin panel. So
Oh, okay.
wait, what did I call the chat?
Meta, something meta.
Meta. Yeah, meta. Okay. Meta challenge.
Right.
So yeah, let me open up. I'll open this up on Etherscan, so I could show you how to use Etherscan. So you see, this what I was solving, I think this is Buckeye CTF. It was a reentrance attack, so I had to deploy a smart contract to exploit this vulnerability.
Right,
So you see, here's this contract creation event,
yeah.
or transaction, I should say. So if we actually look at this transaction, the entire contract is going to be encoded in the transaction data. So we can view this as just plain text here.
But the remains.
And if we look carefully, I've encoded
Oh,
this
wait,
in the actual
0.0.
contract.
I could blame it. That's
So yeah, it's sort of a contrived challenge.
I was trying to
Yeah.
like people know. the
Well, I mean, I'll have to
restart,
restart.
so it wasn't working. It's like,
Yeah,
give me an-
I mean, that's one way to do
Can I
it,
add
but
something?
it is in plain
I have to,
text
like,
in the contract bytecode.
I see.
I wrote exactly what you wrote.
If we wanted,
What is that thing?
if we wanted to view the code of the deployed
Oh, wait,
contract.
5
we
seconds
do that as
more, I
well.
guess.
Yeah, so I can show you. So you see this 2 here. This is the contract address. And you can view that here. So this is the actual bytecode. You could switch to the opcodes view. So this will be like the actual, basically, this is the EVM assembly.
Okay, so there should be like a push 32 or something.
That's all I need.
Yeah, let's see. Where is?
0.05.
I'm not sure. Wait, what's the ASCII code for like the I don't know, like opening bracket?
Okay. I could just read 3D or something.
3D.
I don't want anyone else to be on the same network.
I don't know if any of these are the string. I don't know. I mean, I guess if you were to disassemble it, you could see it somehow. Or if you just dump the thing with strings,
I know.
it'll show up that way as well.
It's basically.
Yeah, because when you
The
said
thing is
decompile,
that
bytecode
you're
just doesn't work.
in-
Yeah, I don't think the decompiler is that up to date.
But that means anyone can technically
Yeah.
get to this contract.
Oh,
But
I
if
didn't do
like,
anything weird. This is
like,
just standard.
hardwire my tools here, and I essentially made that like I'm the only one that's like what is
On what?
and then
On the contract page?
Yeah. Never mind.
Oh, on the transaction? Yeah. Yeah, so this includes the contract.
Wait, Jake,
Yeah.
how did you deploy it?
What?
How did you deploy it?
I deployed it through Remix.
Well, yeah,
Wait, what do you
I
mean?
know that. I put some stuff in like my room chat. And then I try to like deploy it. But I didn't have, I had some. There was a
Meeting with the
That should be enough.
Wait, value is no, that's a guess.
It's pretty.
Is it getting
It's real. These are just that.
because we don't.
Then you just get us.
We're getting close.
Then you deploy it.
Waiting?
Okay, should be. Just check if it actually. I'm so close. We're so close. All right, we just need. I hope it's there.
Okay, now I could run this. So perfect.
Oh, wait, don't press that. Press on. Yeah, it gives you this.
like 2 nights ago.
Yeah.
I
think I just like sectioned it only to this.
Yeah, so yeah, solve that. Okay, so just also solve that. This those are the so yeah, and
So what are you looking at that?
Alright, so.
I'll get past the I just solved it. Press that.
And it's very fast.
Just wait for the mouse, press on it.
That's crazy. Finally, okay, I understand the word.
Okay.
Well, I mean, you gotta say.
Do you want to say anything in public? Oh, yes. Resource at the end of the slides are good. Good setting point.
Oh, yeah.
I don't know.
Excuse me.
So I just pull those up.
Yeah.
Oh, sorry.
That's so close. Yeah.
Okay, I understand.
Wait, where's
Just
the?
need to connect to this.
Yeah, so I'll just go down.
Then I could just deploy. Okay, I could do solidity challenges.
I guess this basically wraps up the meeting. Just if you want to learn more about this stuff, I know I went over everything like really fast. It took me much longer than that to actually learn all this. Check out the Ethereum docs and white paper, and then these other resources as well. Yeah, what's up? Yeah, I'll pull that up.
What code is
So this is the link that you get, right? So this was my wallet address when I was competing in Buckeye. So what we have here is this contract creation. So if we want to look at the actual bytecode here, we can actually see in this contract creation transaction, this is the contract source, or not the contract bytecode. So if we want to view this as a string, we could just switch this to UTF-8 and yeah, so this is it's encoded in the actual contract source code. It's pretty contrived, but I just want to make sure like you could poke around like Etherscan.
No, that's really good.